So yeah, so thank you for showing up. I hope you guys are not very anxious about the midterm, and even if you are, I hope this session will help you out with that. So the agenda is basically we'll go over some of the topics that we have covered so far in the class, and we will try to like summarize each and everything in one place. Okay, so let's start. So these are the main topics that you have to basically study for the exam. And also, like, before I go deep into this topic, if at all, like, if my voice breaks or if you're not able to see my screen, please interrupt me in between. I will also try to keep track of the chat, but in case I'm not able to, please feel free to unmute yourself and ask the question. Okay. So the first, is there a question? Okay. So the first thing that we have to keep in mind for the exam is the order notations, that is big O, small o, theta, and omega. So go over the lecture notes once again, go over your homeworks, and make sure you understand these terms clearly. You might see some questions regarding these in MCQs or true and false. Okay. Sorry? Is there a question? Okay, so I think professor has already mentioned this. So you have like three type of questions basically. One is MCQ slash true false kind of question. Then you also have something like a counterexample type of question. Like you will be given some arguments and we'll probably ask you to give some kind of counterexample to that. And you'll also have a design problem basically. So you will have to design an algorithm to solve that particular problem. So these are the graph algorithms that we have seen in the class until now. The first one is this explore algorithm, that is graph search. So you're basically given a graph and a vertex S, and then it basically returns all the reachable vertices from that S. So the main point to note here is this G and the vertex S. And then there is this DFS, depth first search. So DFS and BFS, they are kind of graph search algorithm. So you have this bigger umbrella called search algorithms, and DFS and BFS are some part of that. Okay. So in DFS, what you do is like we explore all the vertices in a stack like operation. Like we go and travel the whole path until we exhaust every set in that, and then we backtrack and we go to the other one. So the runtime for DFS is big O of B plus E. And in breadth first search, so in breadth first search, we are given unweighted graph G and a starting vertex S, and then it returns the shortest path to all the reachable vertices. And the runtime for that is also V of E. So in BFS, we kind of use a queue-like structure. So it travels layer by layer, and that's why we are able to get the distances in that algorithm. Dijkstra's algorithm is the shortest path algorithm. It starts from a vertex S, and then it gives you the shortest path to all the vertices that are reachable from S. And we have seen Dijkstra's algorithm has two types of implementation in general. So the implementation is heavily dependent on this priority queue. So if you use array as your priority queue, then the runtime is big O of V square. And if you use a binary heap, then it is V plus E log V. So just make a note, like, these algorithms, the working of this priority queue and the runtime associated with that, because it's very important when you do the runtime analysis for these algorithms. And then we have these two MST algorithms. In MST algorithm, we basically try to get a connected tree-like structure where every node is connected and we don't have any cycle, and the cost of that tree is as low as possible. Okay, so a minimum spanning tree. So in prims, we start from any random vertex and then we keep on increasing that subset until we cover all the vertices, and we always pick the shortest edge coming out of it. In Kruskal's, we pick the lightest edge first, and then we keep on picking the lightest edge in the order. And we also check if it is not forming the cycles, only then we add that vertex to the set. Okay. So the runtime for both Prim's and Kruskal is similar. It is E log V. The underlying difference is the data structure that we're using here. So Prim's is very similar to that of Dijkstra's. And in Kruskal, we have seen the best implementation using DSDS. Okay, so make sure you know like how DSDS works. Basically, like how. I think we have seen two type of implementation there in Kruskal's. One is a leader-based method. Another one is a union-based method. So make sure you know like how these algorithms work. Any question? Anything here?
I have a clarification question.
Yeah, go ahead.
So for the primary difference between graph search and / Explorer and DFS is that for Explorer or graph search, in an undirected graph, you will stop once you've explored everything inside of S's connected component, right? You'll stop
That's right.
after that.
Yeah.
Whereas in DFS, you visit everything. So you're able to determine all the connected components in an undirected graph.
Yeah, that's a good question. Actually, my next slide comes to that. I think a lot of students, they have this confusion with DFS and Explore. So I hope like after this slide, your doubt will be cleared. Okay.
Okay, thank you.
Yeah. So in Explore, as you said, like in Explore, it basically takes two parameters its input. One is graph, and another one is the starting vertex S. And yes, it only gives you a connected component in this case. If it is an undirected graph, it will give you everything that is connected to S. But in DFS, it's a little bit different. So if you say like run DFS on G starting at vertex S, it is very similar to Explore. In that case, it is exactly Explore. So when you write DFS from G starting at X, these two are same things. Okay. But when you just say DFS without any starting reference, so this is like a textbook definition of DFS. And in this case, these pre and post numbers are generated. And this function, it will run explore until all the vertices are visited. So in case of DFS, if you only give graph as your input, as your parameter, then it will explore all the vertices inside of that. Okay, so in that case, what happens is like you have like different connected components like this, right? Each have their own post and pre-orders, each node. Is it clear?
Yes, thank you. So it is kind of confusing that they both have the same name, but you just distinguish between the two different kinds by the parameters.
Yes. So actually the problem with DFS is that in a lot of materials, they have like their own definitions. So to be consistent in this class, we are going with this definition. Okay. Any other questions?
Wait, so sorry. Just want to clarify. What definition is that? Is that just taking the input G?
Yeah.
Okay, understood.
Yeah. I see one question in chat. How is it able to get a post and pre-numbers if you don't have a starting vertex? So when we just have a G, so in that case, actually, we give you a tiebreaker what to choose when. So sometimes what we say is like you just traverse your vertices in the alphabetical orders. So we start with the most smallest element. Okay. So in many cases, it's A or B or whatever the smallest alphabet is. And from there, we started. So when we just visit the vertex for the first time, we assign a pre number to it. And then when we like backtracking, at that time, we assign a post number to it. Okay. So I hope this distinction is clear. It's very important, like whenever you're writing your algorithm, you know the difference between these things so that there is no ambiguity. Okay, let's go on to the next topic. So we have basically three types of graph. I would just say two types of graph. First one is undirected graph, in which you do not have any direction from your. So if there is A and B connected with an undirected edge, you basically can go from A to B or go from B to A. Both is fine. But in case of directed graph, the edge is directed here. Okay, so now you can only go from A to B. You cannot go from B to A. And the concept of strongly connected component, metagraphs, and backward. So these are the edge types. It comes in your directed graph. So make sure like you understand like this definition, what is forward, backward, and cross edges. Okay. So so these distinctions and all these definitions, they come in your directed graph. And then we have this DAGs, basically directed acyclic graphs. Here we do not have any cycles. So that's I'm sorry, was my audio broken in between?
Yeah, it was. We can hear you.
What was the last thing I was saying? I'm sorry about this. Was I talking about DAX? Okay.
Directed graphs.
Cool. So in directed graph, we have SCCs, metagraphs, and all this definition of different type of edges. So one special graph in directed graphs is this DAX. So in DAX, we do not have any cycles. And that's why we have these things here: sources, sinks, and linearization, like the topological sorting algorithm. So make sure you also go through these things, like how to linearize a acyclic graph, a directed acyclic graph. This might help you out in solving a lot of problems. Okay. And we also are using like data structures intermediate in these algorithms. Like in Dijkstra's, we are using priority queue. In MST, especially in Kruskal's, we are using disjoint set data structures. So make sure like in priority queue, you understand what exactly make queue is, what is the runtime of make queue, what is runtime, and implementation of insert, delete, mean, and decrease key. So the runtime is very important, and the kind of operations that they are doing under the hood. So make sure you understand these as well. And also a different implementation of these priority queues, like what is the difference between array and binary heap, like how the runtime changes, what happens when a graph is sparse, what happens when graph is dense. Okay. So these are like important things that you need to understand for these problems. And also, like if a problem is given to you, you should be able to identify which one to exactly choose to get the best possible runtime. Okay. And DSDS is basically what we use in Kruskal's to optimize our runtime. So make sure like you understand how this make set is formed, how union is done, like in union, how you are like doing a union of two different trees. How are you finding the root node of any given vertex? And what is the runtime of that? Versus the leader approach, in which we are simply using a array and then we are just assigning the leader, and in case of union, we are just traversing the whole array and then replacing the parents. Okay. So the important thing here is the runtime of each operations. And I again want to like emphasize a little bit more on these notations. Make sure you understand what these notations are. Your runtime depends on these notations. Yeah. Any question in this one? Okay. So in midterm 1, we have graph problems basically. So I think the most challenging part of the midterm might be the design problems. So try to like create a reduction based algorithm, like understand each and every algorithm that we have covered in the lecture so far, and try to avoid modifications if possible, because modifications they require very extensive proof, and you won't be able to rely on the algorithms that we have covered in class. So it's always suggested that you use a reduction based algorithm. So in reduction, what we do is like we create a new graph that captures all the properties, and then we run some known algorithm that we have already covered. Okay. And also make sure like you create so if you are running a graph algorithm, always make sure that you create a graph first and then you run the algorithm. For example, if you are given a matrix or a table, you cannot run DFS or Dijkstra's directly on that. So make sure you define what your graph is, what are the vertices, what are the edges. So these definitions are very important. And yeah, you always try to go with reductions. It's easy to prove and yeah, easy to do the runtime analysis and everything in here. Any question here? Okay. So resources to study for the exam. So the homework problems, they are a very good reference to everything that we have covered. If you are diligently doing your homework still now, I don't think you will have any problem with the midterm. And also refer to the problems from discussion sections. Just a second, let me try to connect to a different Wi-Fi. Okay, can you hear me, guys? I'm really sorry about this. Just need a confirmation before I start. Yes, the slides are already there on Canvas. I will also try to like upload the annotated one later on. But yeah, you can find these slides on Canvas now. I hope I am audible now. Okay, we also have shared this practice exam problems with you guys. So the difficulty of the exam is going to be pretty similar to these practice problems, though it is not going to be as lengthy as the practice problem, I guess, but you can count on the difficulty. So any questions till now? So what we will do next is like we will go over some questions and we will see how to apply the graph algorithms and how to do the proof and do the runtime analysis. So if you have any questions before that, please let me know. Okay. Oh, before that, let's do this proof review. It's a very important topic, and I think a lot of students are confused about this, like when to use which proving technique. So whenever you are given like a returning true or false kind of algorithm, so what you generally do is you create a new graph G prime, and the goal here is to use some kind of correspondence between this G and G prime, right? So whenever you are given some true and false kind of questions, what you do is like a bidirectional proof. So it's basically a if and only if kind of proof. So the keyword here is to show this correspondence between your graph G and G prime. Okay. And then we have another proving technique. It is this optimization proof. So in this optimization proof, we show two things, that is existence and the optimization. So in existence, we show that we have a solution which satisfies all the properties that the problem statement is asking you for. So in this as well, we sometimes use a bidirectional proof, right? Because what you are trying to do here is like, so if suppose the question is asking you to find a minimum path from S to T, first you want to show that there is a path from S to T, right? So in that case, like if you have a modification from G to G prime, then you want to show the correspondence between these two graphs. And in that case, we generally use a bidirectional proof. Okay. Like if there is a graph in G, then there is a graph in G prime as well. Okay. So existence, and then you have optimization. So a lot of time we ask you to find a minimum value or a maximum value. And you want to show that the values that your algorithm is returning is actually the best possible value. You cannot do better than that. In that case, we basically what we do is we do optimization proof. And a lot of time you might have seen, like even in the discussion sessions or your homeworks or your lectures, you use this contradiction to prove that sometimes. Like if it is not straightforward, then you do like some kind of contradiction. You assume the other thing and then you show that it's not possible. Okay. And a lot of time you rely on these known algorithms covered in lectures to prove your optimization proof. Is there any question regarding proofs and proving techniques? Is it clear? Oh, and we,
Sorry,
yeah.
do you have a specific homework question number that covers bidirectional proofs and optimization proofs? Like, do you know which homework does which one?
So for optimization, you can look at Dijkstra's algorithm. So there we actually show, the path that we are getting, the list of V. It is actually the best possible path. So I think we compare this D of S and dist of S there. So this would be a good reference to see the optimization proof. And for bidirectional proof, I think we covered it in first couple of weeks, where we create copies of your vertices and you add the edges. I'm not exactly sure which homework or question number that one is, but there you can see the bidirectional proof actually. We might see some of this proof today in the problems later on. And then we also have this loop invariant. So the loop invariant is basically used like whenever we have these iterative algorithm, like where the value is getting updated every iteration. So in that case, we use a loop invariant. But mostly, these are the algorithms that you have to be clear about, these two. Any other question? Okay. So let's see these problems. I think this is there in your practice problem. I'm not sure if it is. So what you are given here is a graph G, a directed graph G, and vertices M edges, and each edge is either labeled with 0 or 1. So these are like weights given to the edges. You're also given two vertices S and T, and you want to determine if there exists a path from S to T such that no two one edges are there in row. So something like this. So if we have path from S to T and these are the intermediate nodes, so we can have something like this. But we cannot have something like this. The consecutive edges should not be 1. Is it clear? Like going from this node to this node to this node is not allowed because we have this unlabeled edge in consecutive fashion. So we want to create an algorithm that runs in O of n plus m, and it should be able to give us like if there is a path that exists. We can also write it like this. It's basically big O of v plus big O of e. So like this might give us an idea that we have to use something like an explore method here. Any hints? Anything? And these edges are directed. Okay, let's see the solution for this one. So this is the high level description. So here also we are trying to make like a new graph G prime. And then we have two sets of vertices, V prime and V double prime. which are basically two copies of this vertex V. So for every vertex V in the graph, we create these two copies, V prime and V double prime. And then we connect them in this fashion. So for every edge UV that is labeled 0, we connect U prime to V prime and U double prime to V prime. And for every edge labeled 1, we simply connect U prime to V double prime. So if you want to imagine it, you can imagine it like this. So we basically have two sets. This one is, let's say, A prime, B prime, some K prime. And here we have A double prime, B double prime, all the way till K double prime. And if the label is 0, this one, then we simply connect in this fashion, or we go from here to here. Okay. And if this label is 1, that means we connect U prime to V double prime. That means, let's say we have U and V here, and there is an edge UV. So we will connect either this to this one. No, in this case, the red edge won't be here. It will go to this vertex here. I think I created this edge in a wrong way. It should be like this. Like this. Okay. So in here we had this edge from A to B. So if it is from A to B, this implies we either connect A prime to B prime, or we connect A double prime to B prime. And in this case, we connect U prime to V double prime. Okay. So we can observe here that in case of edge labeled 1, we have connection from this set to this set. And in case of 0 labeled edge, we have connection either within the set 1, or we connect it from the set 2 to set 1. Okay. And after that, what we do is we simply run explore from S prime, and then we check if T prime or T double prime are visited, and we simply return true. And if none of these are reachable, we return false. Is this algorithm clear?
No, I'm getting confused on why we need to create two sets of vertices.
Oh, okay. Yeah. Let me, so you got the question right. So in a path, you should not have consecutive one label edge.
Yeah, that part makes sense.
Yeah. So we want to keep track of the last vertex that we have seen, or the last edge that we have seen. So let's say you are at a particular node U, okay, and you have a bunch of nodes coming out of it. But if you know that what was the last vertex that you took to reach at V at this particular vertex U, you can make your next choice, right? So let's say if it is 0, that means you are allowed to choose whatever you want. It can either be 1 or it can either be 0. That's fine. Okay. But the problem comes when this is 1. Now, in this case, you can only choose the edge labeled 0. Right? So this vertices with double prime notation, they basically tells you that the last edge that you have seen till now, or the last edge that you have seen in the path, is basically one labeled edge, right? Because you are at this V prime only when you encounter a one labeled edge. Whereas when you encounter a 0 label edge, you always are at this first set. Does that make sense? So when you are at this first set, you can either go to 1 or 0. It doesn't matter.
Wait, so inside the brackets, the left side set of brackets is V prime and the right side set of brackets is V double prime?
Right, yes. So if you are at this this set, that means the last edge that you saw is one labeled edge. And that means now you can only go from the set 2 to set 1. Does that make sense? And this blue edge, it actually represents that. Because the problem would be if you are going from A prime double prime to B double prime, this will be a problem, right?
Yeah, that's two one edges connecting, right?
Yeah. So we do not have these kind of edges here, right? In the definitions, if you look at this, we do not have anything like this. So that's how we are avoiding taking the consecutive one labeled edge. Does that make sense?
Oh, okay. I think I get it.
Okay.
Yeah.
Cool. So coming to the proof, so yeah, it's a bidirectional proof. It's basically a true or false kind of problem. So that's what we saw in the proof review. So the forward direction is basically if the algorithm returns true, that means there exists a path from S to T that does not cross two edges in a row. And the backward direction is the algorithm returns false. That means there does not exist a path from S to T such that two one edges are crossed in a row. And this is basically a contrapositive of this first statement. So what contrapositive means is like if A implies B, that means not B implies not A. So if this first statement, if it is A, and the second statement is B, then this line here, it is basically not B implies not A. So there does not exist a path. So the not of that would be there is a path from S to T, and returns false. The opposite of that would be return true. Okay, so these two statements, they are equivalent of each other. Are you clear with this forward and backward directions here? Okay. So let's see how we'll prove this. So in the forward direction, what you do is like you assume that the algorithm returns true. And that means like there is a path in graph G prime. And you want to show that this implies that there is a path in G as well. Okay. So we won't go into the exact details of this problem, but we know that we return true only when T prime is visited or T double prime is visited. In either of these cases, we return true. So if you look at the proof in detail, you will see that we are trying to use contradiction to prove this. Like we say, like if we assume that it contains two consecutive one edges, then we show that it's not possible. And that's how we prove these things. And similarly, in the backward direction, we show that if there is a path in G from S to T that does not contain two consecutive ones, then it returns true. Is it clear in this one, like how we are doing these proofs? Okay. So what I tend to do is like whenever you are trying to prove this bidirectional proof, always assume your left half to be correct and then show that it corresponds to the right half. Okay? I'll always say that, let's say this A is true, and then you try to prove that this B is also true. So that's the rule of thumb that I generally use to prove these things. Okay. If you don't have any question in this one, let's take a look at the second problem. Oh, before that, we need to do runtime analysis. Yeah. So what is the order of vertices in here? It's big O of 2v because we are making two copies of each vertex. And similarly, the number of edges would be big O of 2 times e. So creating a new graph G prime is big O of 2e plus 2e. And explore, it will take big O of 2v plus 2e. Right? So in the end, the runtime would be Vico of V plus C. Any questions here? Okay. So this problem is a little bit interesting. So it's called a gray coloring problem. So we are trying to color this vertices with a gray coloring scheme. So the problem, it goes like this. So we have a directed graph G with no self loop. It is a simple directed graph. So you want to design an algorithm that returns maximum number of shades of gray necessary to make a gray coloring scheme of G. And these are the restrictions. That for any edge VU, U must be at least as dark as V. That means if you have a direction from an edge from V to U, that means U must be the same shade of V or darker. Okay. So let's say we are defining our shades with these numbers. So 1, like 2 being darker than 1, 3 being darker than 2 and 1. So if V has a shade of I, then the shade of I should be greater than or equal to I. Okay. So the question is, you want to maximize this number of shades here. You want to color your graph in such a way that the total distinct shade of gray that you're using is the maximum possible number. How will you do that? So what is the first thing that is coming to your mind? I already see a solution in the chat. Someone is saying number of SCCs. We are going to do a very similar thing. Yes. Any other idea? Okay. So let's jump on to this SCCs and see like how it will help us out. So let's observe some properties here. So the first property, it says that if a set of vertices that can be reachable from each other, then they should be of one shade of gray. What that means is like if there is a path from U to V, and you can again go back to U in some way, okay, then these two should be of same color. That's what it is saying. And you can see why it's true. So let's say this is 0.2. So this one is either 0.2 or greater than that. So let's say it is 0.8 now. So eventually what will happen is like 0.1, 1, 1.2. So this one should be greater than 1.2, but it's not, and that's an inconsistency. So that's why the best thing that you can do is you have to keep these shades together, the same. So if U and V, they are in the cycle, that means let's define this color by C. So C of U and C of V should be same. Okay. And the second observation is that two vertices which are not both reachable from each other can be of distinct shades. Like if there is a path from U to V, and U is U is not reachable from V, then if this is C of U, then this can be greater than or equal to C of U. Right? This greater than is the main observation here. But in this case, it has to be strictly equal. Is it clear? Why these observations, they make sense? Okay. So the algorithm is pretty straightforward. Run the SCC algorithm and then return the number of strongly connected components. That's it. So that's your answer. So the challenging part here is the proving part. Like, how do we prove this is actually correct? Like, how do you prove like you cannot have more than the SCC number of shades? So let's see. So there are two primary things that you want to prove here. First one is you want to show that all the vertices in the same SCC must be colored the same shade of gray. Yeah. So this is kind of an upper bound on that the property that we have. And in second one, we want to show that if we linearize the SCC and shade them in increasing darkness, then we have a valid gray coloring. Okay, so we have these SCCs. So I'm creating this meta graphs, let's say something like this. So first we want to show that everything in this circle, they are colored by the same thing. Okay. And the second thing that we want to show is that if we linearize these SCCs using a topological sorting, then or something like that, using a post number, something like that, then we have a valid gray coloring. So let's see how we'll do that. So the first proof is pretty similar to the illustration that I showed earlier. Like if there is a cycle, that means both of them have to be of the same color, and that's exactly what they have done here. So what they are saying is like, let's say that there's a path from V1 to Vk, and it's part of the same SCC. That means there is a path from Vk. I think I cut out again here. I hope the recording will be proper. I just hope it's not getting cut out in between. Okay. So where was I the last time, like you guys could hear me? Was I at this point? Like I was explaining like why the vertices in the same SCC, they have to be. Okay. So the first thing that is the same thing, like everything in the same SCC, they have to be same shade of gray. And the second one is like, if we linearize the SCCs, then that will be a valid gray coloring, right? Because if there is a path from U to V and you're not able to come back, that means you can obviously color V with a different shade. So yeah, so this is the general idea of the proof here. So later on, you can go and see the exact proof, like how they have done it here. It will make more sense. And runtime of an SCC algorithm is simply big O of P plus E. Okay. So we still have a couple more minutes. I think we can go over one more problem. But before that, do you have any questions? Yeah, these slides are up there on Canvas. Yeah. Okay, so problem 3. So you are given a maze represented by connected undirected graph G, where edge weight, they represent like how long it takes to go from U to V. Okay, it's basically the time. The cost here is the time. And you're also given two vertices S1 and S2. So you start at S1 and your teammate, it starts at S2. Okay, you start at S1, teammate, it starts at S2. You want to find each other. That means at each point, you and your teammate can either stay put or traverse through an edge. So you will start from here and the teammate will start from here, and you meet here somewhere in the middle. So what you want to do is like, what is the fastest time it will take for you to meet up? How will you solve this graph, this problem? Any ideas? So it is kind of like a shortest path, right? Let me think. Would Prim's algorithm work? Prim's algorithm won't give you the shortest path, so that might not work in this case. Because the first problem is like you don't know which vertex you are looking for, right? This U can be any vertex in the graph G, except for S1 and S2. Oh yeah, Dijkstra's, that's a good start. Okay, I see a solution saying run Dijkstra's on both S. And so what you're looking for in that case? So if you run Dijkstra's from both the S's, what is it that you're looking for? You still don't know which point you're going to meet at. You need to find that point as well, right? Somehow. So the one way could be, yeah. Is someone saying something? So the one way could be like you run Dijkstra's from S1, you run Dijkstra's from S2, and then you check for each and every U possible, like what is the time that each of you are taking to get there. Yeah. And since we know that you can actually stay put as well, like you don't have to reach there at the same time. Like if someone reaches there earlier, then they can just wait it out until the second person comes in, right? So you want to find the max time. So yeah, so we'll do something like that only here. So let's say you are starting from Warren Hall and someone is starting from your GH Hall and you want to meet at Price Center. So for you, it takes 5 minutes. For your friend, it takes 7 minutes. So the final time, what will it be? So this person has to wait for 2 minutes, right? So eventually, by the end of 7 minutes, you both will meet. Make sense? So now what we'll do is like, we will check for each and every possible intermediary points that are both reachable from S1 and S2, and we will find which point is giving you the minimum possible time. So yeah, again, very straightforward idea here. So what we are doing is we are running Dijkstra's from S1 and S2. And then for every vertex U that belongs to V, we calculate this property du for that vertex. That means max time, max of time that it is taking for both of you to reach there. And then we simply return the minimum possible value from all these du's. Does that make sense? So what do you think, like, what do we need to prove in this case? So understand it is an optimization problem, right? You are trying to find the minimum value. So what is the first thing that you need to show? So you want to show that the answer that you're getting, that the U is actually reachable from both S1 and S2, right? And second thing, we want to show that this minimum of du is the answer that you're looking for. Let's see how we do that. So I think you can take it as an exercise. It's a very straightforward proof. The first part is so I will give an informal proof. So when you run Dijkstra's and the distance is not infinity, that means it is reachable, right? That means it is giving you some quantifiable value to reach that particular point. That means it is reachable, and we have proved that. And second thing is the optimality, and for that you can simply rely on the Dijkstra's, that it will give you the best answer, right? So if you are reaching at point U from S1, that means that's the best possible time that it will take to reach there. So yeah, and in order to do the runtime, it depends on the kind of priority queue you are using. If you are using array, it is V square, big of V square. If you are using Fibonacci heap, it is V log V plus E. And if you are using binary heap, it is V plus E log V. Is everything clear? Any questions? I see one question. To clarify, the vertex U that we are trying to reach from S1 and S2 is known, right? No, we do not know that. We don't know that. And that's why we are checking for all the u's possible. So in the third point, we are going through all of these vertices. And then we check like for every vertex, how much time does it take? And then we return the minimum of all these sets. You run Dijkstra's only from S1 and S2. So let's say you have a graph like this, S1 and S2, and you have these vertices here. Okay. Something like this. So like once you run your Dijkstra's from S1, you know the minimum time it takes to reach this particular point U1 from S1. And in the second Dijkstra's, you run it from S2. So now you know like how much time it takes for your friend to reach at U2. And then you simply use this formula to get like what will be the ultimate time for both of you to reach at this particular node. So you only run it once on both the vertices. Because we know the starting point. That's why we don't have to run it on every vertex. Is that clear? Okay. There's one more problem set that we have not covered in this review session is the MST problems. We covered that in Monday's discussion session. So we covered two problems related to MST. I highly suggest you guys to take a look at it if you haven't yet. Before we end, are there any questions that you want any clarifications with? Yes, that's right. So D of U is the time of the slower person, yeah. Because that slower person, because the person who reaches there first, the fastest one, he can or she can, they can wait there for the remaining amount of time. We still have 7 more minutes. So feel free to ask anything, any question that you have. And good luck with your exam, guys. I think the seating arrangement is already posted on Piazza. Please take a look at that. And I will try to post it on Canvas after this session is over. And I hope the recording is not cut out in between. One row. Okay, let's see that problem. First one. This one, right? See if I can add a page here. And, yep. So let me explain the first problem once again. So what we said, like if U and V, they are connected by a zero labeled edge, then what we are doing is we are connecting U prime to V prime and U double prime to V prime. So U prime to V prime and U double prime to V prime. And if U and V, they are labeled by 1, what we do is we connect U prime to V double prime. So the idea here is to look at the last vertex that you have here, last vertex. So if it is a zero labeled edge, you will only be at a single prime here, right? A single dash. And if the labeled is edge, so is labeled, sorry, if the edge is labeled by 1, that means you are at this double prime vertex. So that's the distinction. So that's how like we are keeping track of the last vertex that we saw, or the last edge that we saw. Right? Because once you are at V, you can take any vertex possible, right? You can, let's say there are these 3 possible options. A, B, C, and D, and some of them are 0, some of them are 1. So you are free to take any of them. Whereas in this case, you are not allowed to do that. If this is 0, it's fine. If this is 1, not fine, not fine. This is fine. So now you are not allowed to take these things, right? So let's say like how it is not allowing you to take this U, V, and B1 labeled by 1 and 1. So how will this path look like in your? We cannot travel as a starting point. So sorry, can you repeat that? I didn't get the last statement. V double prime cannot travel as start point, right? No, so the start point is always from S prime. So if you look at this, we run our explore from S prime. So you will never start your graph search from V prime. Oh, sorry, double prime. Like if you convert this graph in your G prime, it will be equivalent to U prime to going from V double prime, or it is possible that you could already be starting from U double prime. So in that case, what will you do? You will go to a V prime. Oh, sorry, it has to go to V double prime, right? In this case as well. Yeah. But if you observe your problem set properly, this edge is not present in the graph G prime. So that's why you will never take this thing. Right? Because if you look at these definitions, this kind of scenario is never encountered. So I hope that one is clear. Please feel free to interrupt me again if you still haven't understood that one. Someone is saying, can you summarize union find data structures? We haven't gone over it much and I'm not sure what they're used for. Yeah. Maybe I can give you a little brief about that, what exactly it is. So if you look at Kruskal's, we have 3 operations that we're interested in. First one is make set. Second one is find. And third one is union. Okay. So this is pretty straightforward. I won't go in detail for this one. You are just trying to actually assign the data structures, like basically initialize it. So in find, you actually have 2 parameters. You're trying to find the parent of these vertices U and V. So let's say there's a graph something like this. And this is U. So you're trying to find this root here. This root is always the parent. So it has a self-loop kind of thing. Okay. And similarly, sorry, it only takes 1. Okay. And for union, you try to do the union of U and V. That means like if there are 2 trees, you belong to this one and V belong to this one. So you're trying to unionize these 2 things. That means you're trying to connect these two nodes, 2 roots. And that's what your union is. And it turns out it is log n operation. This is log n operation when you use disjoint set data structure. N is your number of vertices in this case. Okay. Actually, we are right on time. Guys, if there are any questions, feel free to post on Piazza, or you can also come to our one-on-one sessions or like office hours. Find and union were used to determine when we found cycles, right? Oh, wait. So in find, you are just getting the root. So in that case, you do not care about cycles much. But in union, when will U and V belong to the same root? it will have a case like this, right? So if you find the parent of U, it will be equal to parent of V. So if this is the case, that means they belong to the same structure. Okay, guys, thank you for showing up, and all the best for your midterm. Bye bye.